This is the EdExcel A-Level Further Maths Paper 1, covering the Core Pure module, and this is from the 2025 series. Question number 1. We have the matrix M given by 3, 6, 0, A3, 1, 2, AA, where A is a constant. Part A. Determine the values of A for which the matrix M is singular. For us to determine the values of A for which the matrix M is singular, we need to begin by finding the determinant of M. Once we have found the determinant of M, we can set that equal to 0 because the matrix would be singular, and from that we can find the values of A. Now, for us to find the determinant of M, we would have to expand along any particular row, and in doing so we have to consider the sign convention shown here: plus minus plus, minus plus minus, plus minus plus. Let us expand along the first row. We have plus 3, and then we cover up the first row and the first column, and we take the determinant of what's left over. That would be 3, 1, A. Then we have minus 6, and then we cover the first row and the second column, and we take the determinant of what's left over. That would be A, 1, 2, A. Then we have plus 0. We cover up the first row and the third column and take the determinant of what's left over. That would be A, 3, 2, A. So we have 3 multiplied by 3 times by A, subtract 1 multiplied by A, subtract 6 multiplied by A times by A, subtract 1 times by 2, plus 0 multiplied by A times by A, subtract 3 times by 2. So we have 3 multiplied by 2A, subtract 6 multiplied by A squared, subtract 2, plus 0. So we have negative 6A squared plus 6A plus 12. And therefore, because we are determining the values of A for which the matrix M is singular, we set the determinant of M equal to 0. Hence, we have negative 6A squared plus 6A plus 12 equals 0. Let's find the values of A. From our calculator, let us go to the equation sub-menu. We have a polynomial of degree 2. We have negative 6A squared plus 6A plus 12 equals 0. So we have A which is 2 and A which is negative 1. So we have A equals 2, A equals negative 1. Given that matrix M is non-singular and that the determinant of M is equal to negative 108 and A is less than 0, part B, determine the matrix M inverse. For part B, we know that the determinant of M is equal to negative 108. So we have negative 6A squared plus 6A plus 12 equals negative 108. And if I rearrange, we would have negative 6A squared plus 6A plus 120 equals 0. Let us solve this equation using our calculator. We have negative 6A squared plus 6A plus 120 equals 0. So we have A equals 5, A equals negative 4. A is equal to 5, A is equal to negative 4. And because A is less than 0, a would equal negative only, and that's because a is less than 0. Knowing that a is equal to negative 4, we replace the a with negative 4, meaning the matrix M will be given by 3, 6, 0, negative 4, 3, 1, 2, negative 4, negative 4. Let us now input this matrix M into our calculator to find its inverse. If we go to the Calculate sub-menu, then press the Tab key to go to Matrix. For our matrix we have a 3 by 3 matrix. Let's input this. We have 3, 6, 0, negative 4, 3, 1, 2, negative 4, negative 4. Let's press back and let's return to the calculation. We now need to input in matrix A here. So we have variable, then we go to the fourth option for matrix. We want to use matrix A. We wish to find its inverse. You can see the inverse of matrix M here. We have 2 over 27, negative 2 over 9, negative 1 over 18, 7 over 54, 1 over 9, 1 over 36, negative 5 over 54, negative 2 over 9, negative 11 over 36. Question number 2. We have to determine the exact value of x for which hyperbolic sine of 2x is equal to 3 times hyperbolic sine x. To begin with, hyperbolic sine 2x is equal to 2 times by hyperbolic sine x times hyperbolic cosine x. So on the left hand side of the equation we would have 2 times by hyperbolic sine x times hyperbolic cosine x, and this will equal 3 times by hyperbolic sine x. Rearranging, we would have 2 times by hyperbolic sine x times hyperbolic cosine x, subtract 3 times by hyperbolic sine x equals 0. If I factorize out a hyperbolic sine x from both terms, we have hyperbolic sine x multiplied by 2 times hyperbolic cosine x subtract 3 equals 0. So we either have hyperbolic sine x equals 0 or 2 times hyperbolic cosine x subtract 3 equals 0. If hyperbolic sine x is equal to 0, that means x is equal to 0, and if we have 2 times hyperbolic cosine x subtract 3 equaling 0, from here we can rearrange to say that hyperbolic cosine x is equal to 1.5, and so x will equal the inverse hyperbolic cosine of 1.5. If we use the hyperbolic function definitions, you can see the inverse hyperbolic cosine x is equal to the natural log of x plus the square root of x squared subtract 1, where x is greater than or equal to 1. So we have the natural log of 1.5 plus the square root of 1.5 squared subtract 1. Let's work this out. We have 1.5 plus the square root of 1.5 squared subtract 1, which is 3 plus root 5 over 2. So we end up with the natural log of 3 plus root 5 over 2. Question number 3. We've got this complex number z equals a plus bi, where a and b are real constants. We're given that z over z star is purely imaginary, part A, we have to show that a squared equals b squared. If z over z star is purely imaginary, that means the real part is equal to 0. Now, we've got z which is equal to a plus bi. Z star, the complex conjugate, will equal a subtract bi. So z over z star, that will be given by a plus bi over a subtract bi. And we can simplify this in the same way we would simplify sets. We essentially have to multiply by 1, and this 1 will be the same as multiplying by a plus bi over a plus bi. You'll notice a plus bi is the complex conjugate of a subtract bi. So we have a multiplied by a, which is a squared. Then we have a multiplied by bi plus another bi multiplied by a. That will be 2abi. And then we have bi times bi, which is b squared I squared. For the denominator, we have a difference of 2 squares. We have a multiplied by a, which is a squared, subtract bi multiplied by bi, which is b squared I squared. Let's focus on the real part for now. We've got a squared, and then, recognizing that I squared is equal to negative 1, we've got b squared times negative 1, which is negative b squared. And for the denominator, we have a squared, and here we have negative b squared times by I squared, so that's negative b squared times negative 1, which is positive b squared. So for the real part, we have a squared subtract b squared over a squared plus b squared. And then for the imaginary part, well, we have this 2abi, and the denominator, similar to what we have here, will be a squared plus b squared. The imaginary part is 2ab over a squared plus b squared. We now need to set the real part equal to 0. So we have a squared subtract b squared over a squared plus b squared, which is equal to 0. And from this we can rearrange and state that a squared is equal to b squared. Given also that z multiplied by z star is equal to 50, part B, determine the possible complex numbers of z. For part B, we've got z multiplied by z star, which is 50. So we have a plus bi multiplied by a subtract bi equals 50. And here we've got a difference of 2 squares. We have a squared subtract b squared I squared, which is the same as a squared plus b squared. And this is equal to 50. Knowing that a squared is equal to b squared, we got that from part A, we can replace the a squared with b squared. So we have b squared plus another b squared, which is equal to 50. So we have 2b squared equals 50, b squared is equal to 25, and because a squared is equal to b squared, that means a squared is also equal to 25, meaning a is equal to plus minus 5, and b is equal to plus minus 5. So for the possible complex numbers z, we would have 5 subtract 5i, 5 plus 5i, negative 5 subtract 5i, negative 5 plus 5i. Question 4, Part A. Determine the general solution of the differential equation d squared y over dx squared, subtract 4 times dy over dx plus 4y equals 2e to the 3x, giving your answer in the form y equals f of x. Let us begin by stating the auxiliary equation. We have m squared subtract 4m plus 4 equals 0. On the left hand side, we can rewrite that as m subtract 2 all squared, and this will equal 0, meaning m is equal to 2. Here we have a repeated root, so the complementary function will be given by a plus bx multiplied by e to the 2x. Because we have a non-homogeneous second order differential equation, we now need to find the particular integral. On the right hand side we have 2e to the 3x. So for the particular integral, that will be of the form y equals pe to the 3x. If I differentiate this, dy over dx, that's equal to 3p e to the 3x, and differentiating again, we have d squared y over dx squared, which is equal to 9p e to the 3x. We can substitute back into this differential equation. So we have 9p e to the 3x, subtract 4 times 3p e to the 3x, plus 4 times by p e to the 3x, and this is equal to 2e to the 3x. Recognizing that the e to the 3x is cancelled on both sides, we have 9p, and then here we've got negative 4 times by 3 times p, which is negative 12p, and then we have 4 times by p, which is 4p, and this is equal to 2, meaning p is 2, so the particular integral is 2e to the 3x. The general solution, then, is the sum of the complementary function a plus bx times e to the 2x plus the complementary function 2e to the 3x. Given that y equals 5 and dy over dx equals 12 when x is 0, part B, determine the particular solution of the differential equation. Before we do anything else, what we need to do is find out what dy over dx is. So we need to differentiate the general solution. And we can do this using the product rule. We have e to the 2x multiplied by the differential of a plus bx, which is just b, plus a plus bx multiplied by the differential of e to the 2x, which is 2e to the 2x. And then we add on to this the differential of 2e to the 3x, which is 6e to the 3x. From the first two terms, we can factorize out an e to the 2x, and so we will be left with 2a plus b plus bx, and then we add on to this 6e to the 3x. We know when x is 0, y is 5, so we substitute this back into here. So we have 5 equals a plus 0 times e to the 0 plus 2e to the 0. So we have 5 equals a plus 2, meaning a is 3. And we also know when x is 0, y dash is 12, so we substitute that into here. We have 12 equals 2a plus b plus 0 times e to the 0 plus 6e to the 0. So we have 12 equals 2a plus b plus 6, and we know what a is, that's 3. So we have 12 equals 2 times by 3 plus b plus 6, and that means b is equal to 0. So we can use a equals 3 and b equals 0 and state what our particular solution is. For our particular solution, we would have 3e to the 2x plus 2e to the 3x. Question number 5. Use the method of differences to prove that for n being greater than 2, the sum of 4 over r squared subtract 1 from r equals 2 to r equals n is equal to pn plus q times n subtract 1 over n times n plus 1, where p and q are constants to be determined. To begin with, this 4 over r squared subtract 1 can be rewritten as 4 over r subtract 1 times r plus 1. R squared subtract 1 is a difference of two squares, which we have rewritten as r subtract 1 times r plus 1. Now, if we take this 4 over r subtract 1 times r plus 1, we can rewrite this using partial fractions, and we can rewrite it as follows. We have a over r subtract 1 plus b over r plus 1, and we need to find out the value of a and the value of b. If I multiply both sides by r subtract 1 times r plus 1, on the left hand side we have 4, and on the right hand side we have a times r plus 1 plus b times r subtract 1. Now, to find the values of a and b, we can choose values of r which will allow us to find out what a and b are. If we choose r equals negative 1, on the left hand side we have 4, on the right hand side this term disappears and we will be left with negative 2b, meaning b is equal to negative 2. When r equals 1, on the left hand side we have 4, and on the right hand side this term disappears, leaving us with 2a, meaning a is equal to 2. We know what a is, we know what b is, and so we can state then 4 over r subtract 1 times r plus 1, that is 2 over r subtract 1 subtract 2 over r plus 1, meaning 4 over r squared subtract 1 is equal to 2 over r subtract 1 subtract 2 over r plus 1. So the sum of 4 over r squared subtract 1 from r equals 2 to r equals n can be rewritten as the sum of 2 over r subtract 1 subtract 2 over r plus 1 from r equals 2 to r equals n. When we come to work with the method of differences, we have to substitute in values from r equals 2 to r equals n and add those together. Beginning with r equals 2, we would have 2 over 2 subtract 1 subtract 2 over 2 plus 1, so that will be 2 over 1 subtract 2 over 3. When r equals 3, we have 2 over 3 subtract 1 subtract 2 over 3 plus 1. That's 2 over 2 subtract 2 over 4. When r equals 4, we have 2 over 4 subtract 1 subtract 2 over 4 plus 1. That's 2 over 3 subtract 2 over 5. When r equals 5, we have 2 over 5 subtract 1 subtract 2 over 5 plus 1. That's 2 over 4 subtract 2 over 6. Now, we could continue, but where do we stop? Well, of course we stop when r equals n. So it would make sense for us to work out the last couple of terms. That is to say, when r equals n subtract 1, and then r equaling n. So we have the middle terms, and when r equals n minus 1, we would have 2 over n minus 1 minus 1 subtract 2 over n minus 1 plus 1. That will be 2 over n subtract 2 subtract 2 over n. Finally, when r equals n, we have 2 over n minus 1 subtract 2 over n plus 1. That will be 2 over n minus 1 subtract 2 over n plus 1. If we take a look at the terms which cancel, we have this negative 2 over 3 cancelling with this positive 2 over 3. Then we have this negative 2 over 4 cancelling with this 2 over 4. And consequently, we would have this negative 2 over 5 cancelling with this 2 over n minus 2. And then we would have this negative 2 over 6 cancelling with this 2 over n subtract 1. So in terms of what we have left over, we've got the 2 over 1 added to the 2 over 2, which is then added to negative 2 over n, which is then added to negative 2 over n plus 1. So we've got 2 over 1 plus 2 over 2, subtract 2 over n, subtract 2 over n plus 1. 2 over 1 plus 2 over 2, that's just 3. Then we have negative 2 over n, and then we've got negative 2 over n plus 1. We have a common denominator of n times n plus 1. So here we have 3 times by n times n plus 1. Then we have negative 2 times n plus 1, negative 2 times by n. And so, simplifying, we have 3n times by n, which gives us 3n squared. Then we've got 3n times 1, subtract 2 times by n, subtract 2n, that will be negative n. And then we've got negative 2 times by 1, which is negative 2. So we've got 3n squared, subtract n, subtract 2, over n times n plus 1. The 3n squared subtract n subtract 2, we can factorize that as 3n plus 2 times n subtract 1. For the denominator, we've got n times n plus 1, meaning p is equal to 3, q is equal to 2. Question number 6. F of z is equal to z cubed plus az squared plus bz plus c, where a, b and c are constants. The roots of the equation f of z equals 0 are z1, z2 and z3. When plotted on an Argand diagram, the points representing these roots form the vertices of a triangle. Given that z1 is equal to 2 plus 4i, the area of the triangle is 12. We have to determine the two possible functions f of z. To begin with, if z1 is equal to 2 plus 4i, and we know that this is a root of the equation f of z equals 0, that means z2, which is equal to the complex conjugate of z1, to subtract 4i, will also be a root of the equation f of z equals 0. We have this cubic equation, and knowing what z1 is and what z2 is, we can find a quadratic factor of f of z. That will be z subtract the root 2 plus 4i multiplied by z subtract the other root 2 subtract 4i. We can rewrite this as z subtract 2 subtract 4i multiplied by z subtract 2 plus 4i. And so we can write this as z subtract 2 squared subtract 4i squared. Essentially, you can think of this to be a difference of 2 squares. So we've got z subtract 2 squared, and then here we've got 4i squared, which is 4 squared times by I squared. So that will be 16 times by negative 1, which is negative 16. And we have this minus here, so we've got minus 16, which is positive 16. Z subtract 2 squared, that's z squared subtract 4z plus 4, and then we add on this 16. So we have z squared subtract 4z plus 20. This is the quadratic factor of f of z. Now the third root, that will be given by r, and this will be real. we've got two of the roots being complex. One of the root then will be real. It will lie on the real axis. We begin by plotting the roots on an Argand diagram. We've got Z1 and Z2. Now, there are two possible positions for Z3. We could have Z3 being here. I've labelled that as RA. Or we could have Z3 being here. I've labelled this as RB. It makes sense if we draw the triangles. We've got two possible triangles. We've got the triangle here and the triangle here. And the height of the triangle will be shown here. The base that's going from Z1 to Z2, that's shown in red, it's this vertical line. That will be 4 subtract -4, which is 8. So this has a length of 8. And if I let the height be h of each of these triangles will be identical. We know that the area of a triangle is a half times base times height. The area is 12, and that's equal to a half times by 8 times by h, meaning h is equal to 3. So to find out what Z3 is, we can recognize that we've got this x coordinate of 2, and we add on to it 3 to get this value RA, or we can subtract from it 3 to get this value RB. So Z3 then will equal 2 plus minus 3. To subtract 3, that's equal to -1. 2 plus 3, that's 5. So Z3, that will either be -1 or 5. We have this quadratic factor z squared subtract 4z plus 20. And from Z3 equals R, we can form a linear factor. If we multiply the quadratic factor by the linear factor, we would get f of z. And there are two possibilities for Z3, that's -1 and 5. If we use Z3 equals -1, f of z will equal the quadratic factor z squared subtract 4z plus 20 multiplied by z subtract -1, or quite simply z squared subtract 4z plus 20 times z plus 1. So let's work this out. Z squared times z, that's z cubed. Then we have z squared times 1, that's z squared. Then we have -4z times by z, that's -4z squared. Then we have -4z times by 1, that's -4z. Then we have 20 times by z, that's 20z. Then we have 20 times by 1, which is 20. And simplifying this, we end up with z cubed subtract 3z squared plus 16z plus 20. When z3 is equal to 5, f of z will be the quadratic factor z squared subtract 4z plus 20 times the linear factor z subtract 5. So if we multiply these together, z squared times by z, that's z cubed. Z squared times -5, that's -5z squared. -4z times by z, that's -4z squared. -4z times by -5, that's positive 20z. Then we have 20 times by z, that's 20z. Then we have 20 times by -5, which is -100. And simplifying, we end up with z cubed subtract 9z squared plus 40z subtract 100. So the two possible cubics will be z cubed subtract 3z squared plus 16z plus 20, or z cubed subtract 9z squared plus 40z subtract 100. Question number 7, part A. Express 2x cubed plus 10x squared plus 9x plus 22 over x plus 2 times x squared plus 3 in partial fractions. We've got this expression shown here. For the numerator, the highest degree is 3. For the denominator, the highest degree will be 3 because we have x times by x squared, which gives us an x cubed term. So we have a cubic divided by a cubic. That will give us a constant. We can call that constant a. And what follows will be the remainders. If I think about this x plus 2, if that is my denominator, my numerator will be 1 degree less than that. 1 degree less than a linear will be a constant. Let's call that b. And if I think about the x squared plus 3, if that is the denominator, the numerator will be 1 degree less. For the denominator we've got a quadratic, therefore the numerator will be a linear term cx plus d. What we can now do is multiply both sides by x plus 2 times x squared plus 3. And in doing so, on the left hand side we've got 2x cubed plus 10x squared plus 9x plus 22. And on the right hand side we have a times by x plus 2 times x squared plus 3 plus b times by x squared plus 3 plus cx plus d times x plus 2. We can now find the value of b by eliminating this term and this term, and we can eliminate this term and this term by setting x to equal negative 2. If we set x to equal negative 2, we can work out what the left hand side will equal. On the left hand side we have 2 multiplied by negative 2 cubed plus 10 times negative 2 squared plus 9 times negative 2 plus 22. It turns out on the left hand side we get 28, and on the right hand side this term disappears, this term also disappears, and we will be left with b times by negative 2 squared plus 3. So that will be b times by 7, or in other words 7b, meaning b is equal to 4. And if b is equal to 4, we would there have 2x cubed plus 10x squared plus 9x plus 22 equaling a times by x plus 2 times x squared plus 3 plus 4, which is what b is, times x squared plus 3 plus cx plus d times x plus 2. If we now compare coefficients, let's take a look at the x cubes. On the left hand side we have 2 of them, and on the right hand side we have a times by x squared. That will give us ax cubed, so the coefficient of x cubed then will be a, meaning a is 2. If we now take a look at the x squareds, on the left hand side we have 10 of them, and on the right hand side we would have a times by 2 times x squared plus 4 times by x squared plus cx times by x. So the coefficient of x squared on the right hand side will be 2a plus 4 plus c. We know what a is, that's 2. So we have 10 equals 2 times by 2 plus 4 plus c, meaning c is equal to 2. If we take a look at the numbers, on the left hand side we have 22, and on the right hand side we would have a times 2 times by 3, in other words 6a, and then we have 4 times by 3, which is 12, and then we have d multiplied by 2, in other words 2d. we know what a is, that's 2. So we have 22 equals 6 times by 2 plus 12 plus 2d. And therefore, d is equal to negative 1. We know what a is, we know what b is, we know what c is, and we know what d is. Accordingly, we can state what this expression is equivalent to. We have 2x cubed plus 10x squared plus 9x plus 22 over x plus 2 times x squared plus 3, which is 2, plus 4 over x plus 2 plus 2x subtract 1 over x squared plus 3. Part B. Hence, show that the integral of 2x cubed plus 10x squared plus 9x plus 22 over x plus 2 times x squared plus 3 with respect to x from 0 to 1 is equal to 2 times the natural log of 27 over 4 subtract pi over 6 root 3. With what we have in part A, we can further rewrite this. We still have this 2 plus 4 over x plus 2, and this 2x subtract 1 over x squared plus 3. We can rewrite this as 2x over x squared plus 3 subtract 1 over x squared plus 3. When I combine these two fractions, I end up with 2x subtract 1 over x squared plus 3. So now when we come to integrate 2x cubed plus 10x squared plus 9x plus 22 over x plus 2 times x squared plus 3 with respect to x from 0 to 1, that is the same as integrating 2 plus 4 over x plus 2 plus 2x over x squared plus 3 subtract 1 over x squared plus 3 with respect to x from 0 to 1. So integrating 2, we end up with 2x. Integrating 4 over x plus 2, we end up with 4 times by the natural log of x plus 2. And here, 2x over x squared plus 3, you'll notice the derivative of the denominator is on the numerator, and so integrating 2x over x squared plus 3, that will be the natural log of x squared plus 3. And then where we have the negative 1 over x squared plus 3, you will notice integrating 1 over a squared plus x squared gives us 1 over a times the arctangent of x over a, meaning we'd end up with negative 1 over root 3 times the arctangent of x over root 3. And we wish to evaluate this from 0 to 1. If we now substitute in for our upper limit, x equals 1, we have 2 times by 1, which is 2, and then we add on 4 times by the natural log of 1 plus 2, so that's 4 times the natural log of 3, and then we add on to this the natural log of 1 squared plus 3, so that's the natural log of 4, and then we subtract from this 1 over root 3 times the arctangent of 1 over root 3. For our lower limit, if we substitute in 0, we have 0 plus the natural log of 0 plus 2, so that's 4 times the natural log of 2, plus the natural log of 0 squared plus 3, so that's the natural log of 3, subtract 1 over root 3 times the arctangent of 0. So we have 2 plus 4 times the natural log of 3 plus the natural log of 4, subtract 1 over root 3 times the arctangent of 1 over root 3, and then we subtract 4 times the natural log of 2, and we also subtract the natural log of 3, and the arctangent of 0 is just 0. So we've got 2 plus 4 times the natural log of 3, and this natural log of 4 I'm going to rewrite as the natural log of 2 squared. And then we've got negative 1 over root 3 times the arctangent of 1 over root 3. Now that's equal to pi over 6, and then we subtract from this 4 times the natural log of 2, and we also subtract the natural log of 3. So I've got 2 plus 4 times the natural log of 3, and this term I'm going to rewrite as 2 times the natural log of 2. Then I've got negative pi over 6 root 3, and then I've got negative 4 times the natural log of 2, subtract the natural log of 3. So if we collect like terms, we have 2 plus 3 times the natural log of 3, subtract 2 times the natural log of 2, subtract pi over 6 root 3. And now we can use the power law of logs. So I've got 2 plus the natural log of 3 cubed, subtract natural log of 2 squared, subtract pi over 6 root 3. And so we have 2 plus the natural log of 27, subtract the natural log of 4, subtract pi over 6 root 3. And if we use the subtraction law of logs, what we end up with is 2 plus the natural log of 27 over 4, subtract pi over 6 root 3. Question number 8. A rambler starts a walk at the bottom of a hill at 10 a.m. The rambler walks all the way to the top of the hill and then turns around and walks back down to the bottom of the hill. The differential equation sin t times dx over dt subtract x times cos t equals a sin 2t sin t, where t is greater than or equal to 0 and a is a constant, is used to model the vertical displacement x meters of the rambler from the bottom of the hill t hours after the start of the walk. Given that after 1 hour the rambler has a vertical displacement of 213 meters and dx over dt equals 273.2, part A, determine the value of a to 3 significant figures. Substituting the conditions into the differential equation, we have sine of 1 multiplied by 273.2 subtract 213 multiplied by the cosine of 1, which is equal to a times the sine of 2 times by 1 multiplied by the sine of 1. From this we can find out what a is. We have the sine of 1 multiplied by 273.2 subtract 213 times cos of 1 over the sine of 2 times 1 multiplied by the sine of 1. It turns out we get 150.04, etc. So to 3 significant figures we have 150, meaning for our differential equation we have sin t times dx over dt subtract x cos t equals 150 sin 2t sin t. Part B, hence determine the particular solution of the differential equation, giving your answer in the form x equals f of t. For part B, the first thing we can do is rewrite this differential equation in a more integrable form. We can divide both sides by sin t, and in doing so we've got this differential equation, and I divide each term by sin t as shown. So sin t over sin t is just 1, so we've got 1 times by dx over dt, and then we subtract from this. Well, here we've got cos t over sin t multiplied by x, and this is equal to, well, we have 150 sin 2t, sine t over sine t. The sine t's cancel, leaving us with 150 sine 2t. To solve this differential equation, we can use the integrating factor method. For the integrating factor, that's given by e to the power of the integral of negative cos t over sine t dt. And working this out, well, we have e to the power of negative, well, here the differential of sine is cos, so we have the natural log of sine t, and then using the power law of logs, we can rewrite this as e to the natural log of sine t to the negative 1. Sine t to the negative 1, that's cosec t, so we have e to the power of the natural log of cosec t, which is quite simply cosec t. And so we would have cosec t times x equals the integral of cosec t times 150 sine 2t dt plus c. So we have cosec t x equals, well, here we have the integral of this cosec t times 150, and this sine 2t, that is the same as 2 sine t cos t. And so we have cosec t x equals the integral of, well, here we have 150 times 2, which is 300, and then we've got this cos t. You'd find the cosec t times by the sine t simplifies to 1. So we have cosec t x equals, well, if I integrate 300 cos t sine t, I end up with 300 sine t, and then we add on plus c. And recognizing that cosec is 1 over sine, if I multiply both sides by sine, we can state what the general solution is. That will be 300 times sine t times another sine t, which is sine t squared, plus c times by sine t. Here is our general solution. We can now use the condition t equals 1, x equals 213 to find the value of c. So we have 213 equals 300 times sine of 1 squared plus c times by the sine of 1. From this we can find out what c is. We would have 213 subtract 300 times by the sine of 1 squared over the sine of 1, which is 0.68686, etc. So c is equal to 0.687, and therefore, knowing what c is, we can state the particular solution. That will be given by 300 sine t squared plus 0.687 times by sine t. Part C. Use the model to determine the time at which the rambler will return to the bottom of the hill. The rambler will return to the bottom of the hill when the displacement is 0. So we have 300 sine t squared plus 0.687 sine t equals 0. Factorizing, we have sine t times by 300 sine t plus 0.687, and this is equal to 0. And therefore, we have sine t equals 0, and 300 sine t plus 0.687 equals 0. The first positive solution can be found from here, where we have sine t equaling 0, meaning t is equal to pi, or equivalently 3.14. Let's convert this into hours and minutes. What we can do is pi take away 3, that's 0.14, etc. And if I times this by 60, I get 8.49, etc. And so here, this is the same as 3 hours 8 minutes. And so the rambler returns at, well, starts at 10 AM, we were told that in the question, and then we add on this 3 hours 8 minutes, and that gets us to 1:08 PM. Given that the vertical displacement of the top of the hill is 300.68 meters, part D, use the model to find the value of t when the rambler reaches the top of the hill. Here we would have 300 sine t squared plus 0.687 sine t equals 300.68. Now if we rearrange, we would have 300 sine t squared plus 0.687 sine t, subtract 300.68 equals 0. So now we can solve this equation. As it's a quadratic, let's go to the equation sub-menu. We have a polynomial of degree 2 with coefficients 300, 0.687, negative 300.68. Here we have sine t equaling 0.999, etc. And for the other one, you can see this is even more negative than negative 1. And so sine t cannot equal 1.002. And so we would have to work with this 0.999988 value. So we have t, which will be the inverse sine of 0.999988, which is 1.565, etc. So we have t, which is equal to 1.57 hours. We can find out what this 0.57 hours is in minutes. So from this I subtract 1 times by 60, which is 33.95, etc. So we have 1 hour 34 minutes. And because the time starts at 10 AM, we have 10 AM plus 1 hour 34 minutes, which is 11:34 AM. Part E. Using your answers to Part C and D, give a limitation of the model. For Part E, we've got this 3.14, which is the total time. And if I take the time taken to go to the top, which is 1.57, this will give us 1.57, which is the time for descent. And so what we see here then is the time to the top is equal to the time to the bottom. In reality, the times will be different, and that's because the speeds will be different, and that makes sense. Going up a hill is a lot more difficult than going down a hill. Question number 9. For the first part, the curves with equations y equals 3/4 hyperbolic sine x and y equals hyperbolic tan x plus a fifth intersect at just one point P. Part A. Use algebra to show that the x coordinate of P satisfies the equation 15e to the 4x subtract 48e to the 3x plus 32e to the x subtract 15 equals 0. For the first part, for Part A, we have those two curves intersecting, meaning we would have 3/4 hyperbolic sine x equaling hyperbolic tan x plus a fifth. We will now use the exponential definitions of hyperbolic sine and hyperbolic tan. On the left hand side we have 3/4 times by hyperbolic sine x, which we can rewrite as e to the x subtract e to the negative x over 2. On the right hand side we have hyperbolic tan x, which we can rewrite as e to the x subtract e to the negative x over e to the x plus e to the negative x plus 1/5. We have 3 over 4 times by half, that's 3 over 8. So we have 3 over 8 times e to the x subtract e to the negative x over 1. And this is equal to e to the x subtract e to the negative x over e to the x plus e to the negative x plus 1/5. So we've got 3 over 8 multiplied by, now here I will multiply the numerator and the denominator by e to the x. So we've got e to the x times e to the x, which is e to the 2x. Then we've got negative e to the negative x times e to the x, which is negative 1. And then we've got 1 times e to the x, which is just e to the x. On the right hand side we've got e to the x times e to the x, which is e to the 2x. Then we've got negative e to the negative x times e to the x, which is negative 1. Then we've got e to the x times e to the x, that's e to the 2x. And then we've got e to the negative x times e to the x, which is 1. And then we add on 1/5. We will multiply each term by 40 e to the x times e to the 2x plus 1. This will get rid of all the denominators. So for this term, if I multiply this by 40 e to the x times e to the 2x plus 1, I would have 15 times e to the 2x subtract 1 times e to the 2x plus 1. And on the right hand side, if I multiply this term by 40 e to the x times e to the 2x plus 1, I would have 40 e to the x times e to the 2x subtract 1. And if I multiply this term by 40 e to the x times e to the 2x plus 1, I end up with 8ex times e to the 2x plus 1. So I've got 15 times by, now here I've got a difference of 2 squares. I would have e to the 2x times e to the 2x, which is e to the 4x, and then I've got negative 1 times by 1. Hence I've got e to the 4x subtract 1. And on the right hand side, well, I've got 40 e to the x times e to the 2x, that's 40 e to the 3x, and then I've got 40 e to the x times negative 1, that's negative 40 e to the x, and then I've got 8ex e to the 2x, that will be 8 e to the 3x, and then I've got 8 e to the x times by 1, which is 8 e to the x. So on the left hand side I've got 15 e to the 4x subtract 15, and on the right hand side, simplifying, we end up with 48 e to the 3x subtract 32 e to the x, and therefore taking everything over to one side, we have 15 e to the 4x subtract 48 e to the 3x plus 32 e to the x subtract 15 equals 0. Part B, show that e to the x equals 3 is a solution of this equation. For part B, we can rewrite this equation as follows. We can rewrite it as 15 e to the x to the 4 subtract 48 e to the x cubed plus 32 e to the x subtract 15 equals 0. Now if I substitute in e to the x equals 3, I would have 15 times by 3 to the 4 subtract 48 times 3 to the 3 plus 32 times 3 subtract 15. Let's confirm if this is equal to 0 or not. I've got 15 times by 3 to the 4 subtract 48 times by 3 cubed plus 32 times by 3 subtract 15. It turns out we get 0. And so e to the x equals 3 is a solution. Part C, hence state the exact coordinates of P. For part C, if we have e to the x equaling 3, from this we can state that x is equal to the natural log of 3. And if we use y equals 3/4 times hyperbolic sine x, we would have y equals 3/4 times hyperbolic sine of the natural log of 3. And using the exponential definition of hyperbolic sine, we would have 3/4 times by e to the natural log of 3 subtract e to the negative natural log of 3 all over 2. So we would have 3/4 times by, well, here I've got e to the natural log of 3 subtract, now I can rewrite this as e to the natural log of 3 to the negative 1, and then I divide by 2. So I've got 3/4 times by, now e to the natural log of 3, that's just 3, and I'll subtract from this e to the natural log of 3 to the negative 1. 3 to the negative 1 is a third, so I've got a third, and I divide this by 2. I've got 3/4 times by 3, take away a third, over 2. Let's work out what this is equal to. I've got 3/4 times by 3 subtract 1/3 over 2. It turns out we get 1. So I've got an x coordinate of 3 and I've got a y coordinate of 1. Meaning P would have coordinates natural log 3, 1. For the second part, we have to show that the integral of e to the 1 over x squared with respect to x between negative 4 and 0 is equal to e to the negative 1/4. If we think about this 1 over x, and then if we think about the x squared for this denominator, we know that the integral will not be defined when x is equal to 0, meaning we have an improper integral. So we know that the integrand is undefined at x equals 0. So we've got this e to the 1 over x squared with respect to x, and because we've got an improper integral when x equals 0, we take the limit as t tends towards 0, our lower limit stays as negative 4, our upper limit will now change to t. For us to solve this integral, we will make a substitution, and that substitution will be u equals 1 over x. In doing so, du over dx, that's equal to negative 1 over x squared, meaning dx is equal to negative x squared du. When x is equal to negative 4, we would have u which is equal to negative 1/4, and when x is equal to t, we would have u which was equal to 1 over t. Hence we have the integral which is equal to the limit as t tends towards 0 of e to the u over x squared times by dx, which we've said is negative x squared du. Our lower limit is negative 1/4, our upper limit is 1 over t. Now here, if I take the negative outside, noticing that the x squareds cancel, I would have negative the integral of e to the u du between negative 1/4 and 1 over t. And if I integrate, we've got the limit as t tends towards 0 of negative e to the u between negative 1/4 and 1 over t. So substituting in for our upper limit where we have 1 over t, we've got the limit as t tends towards 0 of negative e to the 1 over t, and I subtract from this. If I substitute in negative 1/4, I've got negative e to the negative 1/4. So I've got the limit as t tends towards 0 of negative e to the 1 over t plus, because I've got minus and a minus, e to the negative 1/4. Now as t tends towards 0, negative e to the 1 over t tends towards 0, so I've got 0 plus e to the negative 1/4, which is quite simply e to the negative 1/4. Question number 10, part A. Given that for n belonging to a set of natural numbers, z to the n plus 1 over z to the n equals 2 cos n theta, and z to the n subtract 1 over z to the n is equal to 2i sine n theta, we have to show that 8 sine theta to the 4 is equivalent to cos 4 theta subtract 4 cos 2 theta plus 3. Now, what we need to do is consider the case when n equals 1, what happens when we have z to the n subtract 1 over z to the n. And the reason for that is eventually I will raise this to the power of 4, so I will end up with a sine theta to the 4. And of course we can get the sine term by raising this one to the power of 4. So when n equals 1, we've got z subtract 1 over z, that will be 2i sine theta, and so z subtract 1 over z to the 4, that will be 2i sine theta to the 4. Now 2i to the 4, that is 16, and then we've got sine theta to the 4 as shown here. So z subtract 1 over z to the 4, that's 16 sine theta to the 4. Now if we consider this z subtract 1 over z to the 4, we can use the binomial expansion to work that is. So we've got 4 choose 0 times z to the 4 times negative 1 over z to the 0 plus 4 choose 1 times z cubed times negative 1 over z to the 1 plus 4 choose 2 times z squared times negative 1 over z squared plus 4 choose 3 times z to the 1 times negative 1 over z to the 3 plus 4 choose 4 times z to the 0 times negative 1 over z to the 4. And if we simplify, for the first term we've got z to the 4, for the next term we've got negative 4z squared, for the next term we've got 6, for the next term we've got negative 4 over z squared, and for the last term we've got 1 over z to the 4. And if we group together the similar terms, we would have z to the 4 plus 1 over z to the 4, subtract 4 times by z squared plus 1 over z squared plus 6. What we can now do is use z to the n plus 1 over z to the n equals 2 cos n theta. So we would have 2 cos 4 theta, subtract 4 times by 2 cos 2 theta plus 6. So I've got 2 cos 4 theta, subtract 8 cos 2 theta plus 6. Meaning we've got this 16 sine theta to the 4, which is what z subtract 1 over z to the 4 is, and this will equal 2 cos 4 theta subtract 8 cos 2 theta plus 6, and if I divide both sides by 2, we end up with 8 sine theta to the 4 equaling cos 4 theta subtract 4 cos 2 theta plus 3. Figure 1 shows the central vertical cross-section of a solid wooden ornament. Figure 2 shows the curve with the equation x equals sine of 1/2 y squared, where y is in between 0 and 8 pi over 5. The region R shown shaded in figure 2 is bounded by the curve, the line with the equation y equals 8 pi over 5 on the y-axis. The ornament is modelled by the solid of revolution formed when R is rotated 360 degrees about the y-axis. The units are centimetres. Part B, using algebraic integration and the result in part A, determine in centimetres cubed the volume of wood needed to make the ornament according to the model. Give your answer to 2 significant figures. For part B, the volume will be given by pi times by the integral of x squared dy. Now we know what x is. That's equal to sine of 1/2 y squared. So therefore the volume will be given by pi times by sine of y over 2 to the 4 with respect to y between 0 and 8 pi over 5. The reason we've got the sine being raised to the power of 4 is because x is equal to sine squared, so x squared will equal sine to the 4. Now if we think about what this sine of y over 2 to the 4 is, we can use the result we found in part A. We can first of all divide this by 8, so I've got 1/8 times by, and you will find instead of us having a theta we've got a y over 2, so I need to replace the theta with y over 2. So I've got 1/8 of cos of 4 times by y over 2, subtract 4 times by cos of 2 times by y over 2 plus 3. So we've got 1/8 times by cos of 2y, subtract 4 cos y plus 3. And so, to find out what the volume is, we can substitute this back into here, So the volume will be given by, now if I take out the 1/8, I would have pi over 8 times by cos 2y subtract 4 cos y plus 3 with respect to y between 0 and 8 pi over 5. So I've got pi over 8 times by a half sine 2y subtract 4 sine y plus 3y, and I need to evaluate this between 0 and 8 pi over 5. So I've got pi over 8 times by, now here I've got half times by sine of 2 times by 8 pi over 5, subtract 4 times by the sine of 8 pi over 5, plus 3 times by 8 pi over 5. So let's work this out using our calculator. I have pi over 8 multiplied by 1/2 times by the sine of 2 times by 8 pi over 5, subtract 4 times by the sine of 8 pi over 5, plus 3 times by 8 pi over 5, so I've got 7.300, etc. So I've got 7.3 centimeters. Given that the density of the wood is 0.85 grams per centimeters cubed and the mass of the ornament is 6 grams, Part C, comment on the suitability of the model. So for Part C, the mass will equal this 7.3 multiplied by the density, which is 0.85 grams per centimeters cubed. So I times this by 0.85 and I get 6.2 grams. Now this is quite close to the 6 grams, meaning the model is suitable.